really tiny, right? Yeah. All right. So you will see that this magnification equation will be the same for lenses, for mirrors, for concave mirrors, convex mirrors. It would be the same for converging, diverging lenses. The same thing with this equation also. 1 over s plus 1 over s prime equals to 1 over f is also the same equation for uh, spherical mirrors, concave, convex, or lenses also, diverging, converging lenses. It's the same equation, but you just have to be careful with the sign convention. If a mirror is diverging, then f is negative. If a mirror is converging, then f is positive. Yeah.
I don't remember if we talked about this, but is there a coefficient to how reflective the mirror?
Yeah, it could be dim or so the more close to 100% it reflects, the brighter the image will be. Yeah. If it absorbs most of it, then it's going to be dim. Yeah. All right, so that's that. So now I want to show you uh, the uh, the shape. I said if it's a spherical mirror, as long as you stay close to the axis, the image will be sharp, or the parallel rays will always be focused at the focal point. But if you're not near the axis, they get unfocused a little bit away. They deviate a little bit from the focal point because of all the approximations with it. What if we want a mirror that actually converges all parallel rays regardless of how close they are to the axis? What shape should it be? You might know, yeah. Flat mirror, you will get a virtual image. It wouldn't focus any, right? Yeah, it wouldn't focus. So we need something that has some concavity. So we're going to do that theoretically. Okay, we're going to come up with an equation, and you will know what the equation is. Can I erase this board here? Yes. I'm going to do it the easy way. I typed some notes this morning. You can do it the harder way, the geometric way, or like more direct way. Uh, if you're interested, you can do it that way. But let's do it the easy way. So here's what I mean. Let's say if you just have a flat mirror, right? Something flat. Let's say I have two rays or three of them, three rays, and they just are incident on the mirror. So they will just hit the mirror and then reflect back. Hit the mirror, reflect back. Hit the mirror, reflect back. They don't get focused at all. They don't get focused anywhere. But now let's intercept them. We're going to place a mirror right here. It's going to have some shape like this. Okay. And let's say the first ray here is here, this one. It will just go down and then go up, right? And then I have another ray, let's say it's here. This other ray, though, it's going to come down straight, but then it can't go all the way. There is something here, a mirror, so it will reflect. How would it reflect, and where would it end up? Like approximately. You would say kind of left, right? correct? Yeah, it will be kind of level. Well, there is a tangent here. You can draw perpendicular. It's going to be something like this. It's going to be in somewhere like this, some, oh, some direction like this. Where these two rays they meet, I'm going to call that the focal point. That's F. That's the focal point. Okay. Now the ray, let's make this one green. The one that comes down this way, let's just take this path here, just this much. For this one also, I should have planned better. Let me erase here. Yeah. Both of them, they start here at the same point. This one gets here, reflects, and this one just comes down and reflects back. Okay. So for the green one, this one, green and yellow are not the best choice. They look very similar on a green board. Okay. So for the green one, it comes down and goes up. So the distance down is F, and then the distance up is another F. So that's 2F. Okay. And I would like the distance traveled by the yellow one to always be to also equal to it. To also be equal to it. Okay. And I want any ray that comes in parallel will converge at this focal point F. So I'm just picking a random one. So some way. So meaning I want the following. I know the distance from here to here is F, right? Let me call this distance this way Y, and the distance this way I'm going to call it X. Okay? The distance X. So what's this distance here in terms of F and Y? This is F, right? So this is F minus Y. Good. So F minus Y. That's on the way down. And then when it reflects this diagonal one. How big is it? Well, it's diagonal, so it's X this way and F minus Y this way, right? This is X, this is F minus Y. That's the diagonal, so I need to square, add, take the square root. So it's going to be this plus square root of X squared plus F minus Y squared. Move these to this side. So you get F minus 2F minus F is F, and then it becomes F plus Y. On the right side, I have the square root of X squared. Let me open this up. So it becomes F squared plus Y squared minus 2FY, like so. And now I need to get rid of the square root. So square both sides. So we're going to square both sides. When you square the left side, it becomes F squared plus Y squared plus 2FY. When you square the right side, just the square root goes away. Get rid of all that. I forget a 2 here, right? 2. Should say 2. Move that 2 here, so you get 4FY is equal to X squared. That means Y equals 1 over 4F times X squared. What kind of shape is that? Parabol. Yeah. So a parabolic mirror will always focus parallel rays at the focal point. Okay? And it's exact, not approximation. Now, a spherical mirror is approximately parabolic when you're near the axis. Why? Well, here's a parabola, right? Near the axis, here, that's basically coincides with part of the sphere, right? That's why if you stay near the axis, like as long as you're around here, it works. But if you get too far, then it doesn't work. Okay. That was just besides the point, but I thought it was an interesting. Okay. So next thing is lenses, converging and diverging lenses. So lenses could be. Would you like additional practice on this, or they're really simple for mirrors? It's good enough. We'll continue to lenses. Okay, we'll continue to lenses. So lenses are made of some material, right? Some transparent material that would allow light to get through it and refract. So maybe glass or plastic. If you wear glasses, they tell you like high index, so they get like thinner glasses. So the index of refraction maybe 1.5, maybe 2, maybe 2.5. I don't know how much it is. But here is how, so lenses. I will just show you how they look like. So a converging, this is called a converging lens. Convex or converging. Lens. Notice for a mirror, when it was convex, it was diverging, right? For a mirror, but for a lens, convex would converge light. Why? Because the light actually goes through the lens. For the mirror, it's reflected back. For this one, the light will actually go through it and then it will refract. The other one was reflection. It's convex or converging lens. Diverging lens will look like this. So basically, a converging lens is always thicker in the middle. A diverging lens is always narrower in the middle, thinner in the middle. Okay. So if you wear eyeglasses, assuming you're nearsighted like me, your glasses will be thinner or thicker in the middle? Thinner. Just look at them. I mean, you can just examine them. They're thinner in the middle, so they're diverging. Okay, they're diverging. We'll discuss why. Okay. So that's how a lens looks like. It could be this way also. It could be like this and then a flat here. That's still converging, as long as it's thick in the middle. Okay. So they can come in many shapes. We're going to consider this kind of shape for us. Okay. This kind of shape. Now, is this just by accident that they cut it like this? Or they have some plan? There is a plan. And we'll get what's called the lens maker's equation. Somebody who makes lenses. Lens maker's equation. It turns out that these lines, let me redraw them on here, and then we will discuss. So this one here. And by the way, the lens itself is not this thick. They're usually much thinner than everything else surrounding them. So this side is part of a big sphere of radius R1. Okay? Yeah. And then this side will be part of another sphere of possibly a different radius. We can call it R2. They don't have to be the same radius. R1 and R2. Okay? And so that's how they're cut. And so these two radii, they don't have to be the same. They could be, or they don't have. I mean, just in general, they don't have to be. And we want to derive an equation that relates this radii of reflection radii of curvature. Okay. Let me draw some images or some rays through these lenses and how they work, and then we'll get to the actual equations. Okay? Let me draw some here, and then I'll come back to this one. I could erase, right? So let's look at the convex lens, how it looks like. Um, So it will have a focal point. Light can go from this side or it can go from this side, either side, okay? There will be some focal point. Doesn't matter which side it comes through. Now, here are the rays that we can draw. If you draw a ray that is parallel, it will go this way. It will go through the focal point. If you draw a ray through the center here, how do you think, what happens to it? It will just pass.
Oh,
Yeah. So it will just effectively go through like so. And if you draw a ray through the focal point, what happens to it? Huh? It will go parallel. And they're supposed to cross. Okay? They're supposed to meet here, if I were more accurate. When they meet, this thing here is the image. That's where the image is. So this is S prime, and this is X. Okay? The image distance, in this case, is positive or negative? Did the image form on the same side as the outgoing rays? No? What are the outgoing rays? These are the incoming, these are the outgoing. So it actually did. So it's positive. It's a positive image distance. Or it's a real image. The actual rays, the physical rays, met there. Okay? I will show you a virtual image now. If the object, as long as the object sits a distance larger than the focal length from the lens, it will be a real image. Let's look at a different situation where the object sits inside the focal point, right? So here's F, both sides, here's F. Let's draw two rays and see what happens. Here's the object. And let's say the first ray, let's make it go horizontal. Where does it go? Through the focal point. The one that goes through the middle will do what? Straight. And you will see that these don't meet. They're kind of going away from each other.
Would it be blurry?
Huh?
Would it be blurry?
It will be a virtual image. It will form a virtual image. Right? So the image, in this case, you see how the image is not on the same side as the outgoing ray. The outgoing rays are on one side, the image is on this side. So this will be a virtual image. The image distance is negative in this case. And the math will show us. The same equation, by the way, will apply here. We will get the same equation, 1 over S plus 1 over S prime is equal to 1 over F. As long as we stick to the same sign convention that we know, we're good.
So if you had something that was like light past your lens, you would see it
What do you mean right past?
like if it
The
was on
object
the
is here?
outside, yeah.
Oh,
But still
the
within
same
the
thing
focal
happens. Yeah, it will be the image then. You can, yeah, let me show you. Yeah. So let's say here's the lens, right? Here's F. Here's F. You're saying if the object is here, right? Same thing. Draw a parallel ray, and it will go this way. Draw a center ray that goes this way, and the image will form from here.
So if I was wearing glasses right now, and there was something that was like right here, where I would see it behind the glasses, or where would I see it?
It depends on your glasses.
Mhm.
Yeah. If it's a virtual image, you will see it. For example, here, this is how magnifying glass will work. Right? It's a magnifying glass. You have a convex lens, and you place the object here, and then you don't see the object through the glass, you will see an image of the object that's larger. And it's on the same side as the object. Yeah. Have you looked at with magnet? Yeah. Mhm.
What's the point of making it both sides curved as opposed to one side curved, one side flat?
You just design, depend how much focal, what's the focal length that you want.
But would it be better to get more focus to make them both curved, or?
Well, it depends. You might want long focal, a large focal point, a smaller focal point, because now you will see, for example, we got somebody who is farsighted, they need maybe a thicker lens, maybe a thinner lens, maybe the material you're using is something else. That will turn that into the engineering and technology of the thing, which I don't get to. Yeah. Yeah. And the reason I don't get to it, we don't have the time, secondly, I don't know. That's the complete answer. Okay, yeah, so we might, okay, I don't wanna spend like 3 weeks on this chapter. We will probably touch on telescopes, magnifying glass, and microscopes. And there is cameras and the human eye. So there is a temptation that you can stay in this chapter for like 3 or 4 weeks. We don't have time to do that. I will have to wrap it up by the next lecture or the next one. Okay. Yeah. Okay. So for a diverging lens, on the other hand, the diverging lens will look like this. A diverging lens will end focus. So let's say I have an object here. A ray comes in. This is the object. If a ray comes in, it's not going to get focused. What happens is it gets diverged that way. Because of this index of refraction in here. So think about it. Let's look at the convex mirror. Let me exaggerate, make it really thick, okay? Like so. Okay? Make it really thick. So let's say I have a ray that comes in, let's say horizontal. This is an approximation, okay? The angle of incidence equals angle of refraction, no. We have n1 sine theta 1 is equal to n2 sine theta 2, right? That's the law of refraction. So now it's the law of refraction. So you have, this is the tangent, and so this is the perpendicular, that's the normal. So this ray, will it bend toward the normal or away? This is a larger index than this, so it will bend toward the normal, right? Just because of refraction, the law of refraction. So yeah, it will bend this way when it gets into the lens. Now it's here. Now draw another perpendicular tangent, a perpendicular, it's a perpendicular. So now when it comes out, will it bend toward or away? Away. Away, because it's a lower index now. It's exiting. It's a lower index. So it will bend away, so it will go like this. Okay? And so it will get through that focal point. Okay? And that focal point depends again on these radii and then the index of refraction. We will do a lab, by the way, next week on these. We have lenses, and it will be a really nice lab. The only thing we don't have is you can't control the radius of curvature. That's why I'm going to do a pre-lab that uses some simulation where you use lenses that you can control the radius of curvature. Okay? And you can control the index of refraction also. Okay, I think I said a lot, but let's get to the math, okay, of this. So the picture is kind of confusing, or the diagram I'm going to draw, because it will have so many kind of rays in it, or like labels, which is kind of a problem sometimes. So let me make my lens like really big, okay? And let me draw my axis here. Okay. let's say the distance from here to here, we will call it Z. Okay, this distance here, this distance this way. I'm going to go, this way is Z, okay? That's Z, okay? All right, so let's say my object is here. Object is here, so that's S. The distance from here, from the object to the lens is S. And the object will send many rays, and we're just going to trace two of them. Wherever they meet, that we'll call that's the image, okay? If you try to trace too many, then you're not gonna get anywhere. You will just get a messy diagram. And that's what simulations are for. You will send many rays and then you will see them converging, okay? So we'll send the first ray will go this way, this way, this way, this way. It will not refract. It will just pass straight, right? Just because of all the angles. Because the angle of incidence will just be zero, right? If it's straight through the middle, it will not bend. So the first ray we get here, okay? And we're going to name, this is S. I'm sorry, that's S prime, sorry, that's the image. This is S. Okay, that's S. Good. Now, the radius of curvature of the lens may be somewhere here, because if you draw the bigger sphere, the radius of curvature might be somewhere here. I don't know where it is, but it will be somewhere here. And then the radius of curvature on this side would be somewhere there, okay? We're going to draw them later. But first, I drew this ray here, the one that goes straight. That's the one that goes straight. And then I'm going to draw another one. I can draw another one here with conversion, and we get there. But I'm going to draw only the one that gets all the way to the edge and then bends to here. Barely touches the lens, just to bend, okay? So we're going to draw it this way. Okay? Make sense? Let's call this distance this way is D1, distance D2, and then D1 plus D2 is the total length traveled by this ray. Okay, this one. D1 plus D2 is the total length traveled by that ray. And then for this ray, the total length traveled is basically S plus S prime, right? The one that's horizontal is S plus S prime. So I'm going to write here L1 will equal to D1 plus D2. Now how much is D1 and how much is D2? Well, D1 would be S squared plus Z squared, okay? Squared. Like so, plus S prime squared plus Z squared, square root for D2, right? Okay. I'm going to factor S squared. So if I factor S squared, I will just get 1 plus Z squared over S, and when I take it out, square root of S squared becomes S. So meaning this, I'm going to have this, S times 1 plus Z over S squared to the 1/2 power, and then plus S prime 1 plus Z over S prime squared to the 1/2 power. Clear? The 1/2 because it's square root. Next, I'm going to use the approximation. This approximation. I'm going to assume Z is much less than S, which makes sense. A lens usually is this big, the object is usually there. So I'm going to use the approximation that Z is much less than S, and it's much less than S prime, and it's much less than the radius of curvature. Okay. The lenses are usually pretty thin. So, meaning this, if z is much less than s, then z over s is much less than 1. And I'm going to use this approximation. If x is much less than 1, then 1 plus x to the n is approximately 1 plus n times x, right? And then plus some other terms, but I don't care about those. Just want to go to first order. Okay. You have seen this equation last semester from me. You have seen it in Calc 2 at some point. Yeah, right. So that's where I'm going to. So I have s times, this becomes 1 plus z over, no, the power is a half, so 1/2. Z over s squared, and then plus s prime times 1 plus z over s prime to the power 2. I forget the 1/2 again. Okay, like so. Multiply through. By the way, this now is an approximation, right? It became an approximation. Just but I will not keep drawing approximation. So now s times 1 is s prime times 1 is s prime. And we're not done, we're not even halfway, so it will take a good while. Hopefully we'll finish it today. Now for this, I have 1 over s squared from here, and then there is an s on the numerator, so it just becomes 1 over s in the denominator. So it just becomes this, z squared over 2s. And then here you will get z squared over 2s prime. Okay. And I'm going to draw a box around this one. Draw a box around that one. Next, I'm going to look at this path. The key is this. Remember, light will take the shortest, the path of shortest time. So if this is a viable path and this is a viable path, then the time it takes to travel through both paths is the same. Okay? The first path is essentially in air or vacuum. It's at the speed of light in vacuum. For this one, it's a reduced speed when it travels here, right? So it travels this far here, plus this far here, plus this far, plus that. Okay? So let me name this this number, this here. I'm going to call it delta 1. Okay? I'm going to call it delta 1. And this small thing here, I'm going to call it delta 2. Okay? Delta 2. Just bear with me. Okay? Is that okay? All right. So now the radius of curvature is here. For this one, this is R2. And the radius of curvature here is R1. Okay. Now, meaning, here is what I mean. I'm running out of colors. So let's call this one here. R1 is just equal to R, capital R1. That's the radius of curvature. If I were to continue drawing a sphere, it would look like that. Now R1 is positive. Why? Because of the sign convention. When the rays go through it, the outgoing rays are on the same side as the radius of curvature, so that is positive. However, this radius of curvature here is negative because the outgoing rays are the radius of curvature is on this side, the outgoing rays are on that side. So R2 will be negative. Similar reason to the convex mirror, where how did the reflected rays go? When we had the convex mirror, reflected rays were going like this, right? But where was the radius? Other side, so it was negative. So R1 is positive, and R2, I'm going to write here. R2 will equal to R2, but absolute value, so it's equal to negative R2. Okay? Because R2 itself is negative minus minus becomes a plus. So R2 is a positive number. It's just a distance. Okay. What are we gonna do then? Yeah.
It's not the radius of the lines?
Uh,
Or is it the radius?
the radius, if I continue drawing it, yeah.
Oh,
Yeah.
I see.
It's like this. Yeah, that's big thing. Yeah. All right, so we need to get this. So let me call this angle here theta 1. And I'm interested in getting this distance, this distance plus this distance plus this distance plus that distance. So meaning this distance here. But this one here, remember, the speed of light here is affected by the index of refraction. That's what you have to divide by the index of refraction. Meaning the time it takes to go through here has to be multiplied by the index of refraction. Because it gets longer, right? The time gets longer because you're traveling at a slower speed. Okay? Does that make sense? So, that's what I'm getting. Okay, so we need to figure out things. This is theta 2. Now, what is this delta, delta 1 and delta 2? First of all, what's the distance from here to here? From here to here. Yes. It's from here to here. That is R1, yes. So from here to here is R1. I'm sorry, that's R1. And from here to here, what would it be from here to here?
R1 minus delta.
I think you're going ahead, just this distance from here to here. It's R1 times the cosine of theta 1, right? This distance is R1 times the cosine, and this whole distance is R1, therefore delta 1 is R1 minus R1 cosine of theta 1. Okay? Let me say it one more time. What's the distance from here to here? R1. What's the distance from here to here? This one?
R1 times cosine.
R1 times cosine theta 1. The difference between them is delta 1. Delta 1 will equal to R1 minus R1 times the cosine of theta 1. That's equal to R1 times 1 minus the cosine of theta 1. Okay? Now, what's the expansion of cosine of theta if theta is small? Well, sine theta is almost equal to theta. But cosine theta would be 1 minus 1/2 theta squared, right? That's the power series expansion of cosine. Cosine, it has the even powers, right? It's